There were some a tiny little bug in this STL file that I had given you. It's Donald 313. It was an hidden symbol inside that file, so he crashed. But it should be fixed now, so it should be okay. And also, I said something wrong last time. Let's see now. Exercise 5 test. And here we are. So, as a test simulation here, I just run the background mesh, you might say, without Donald. And we got constant pressure all over the place, we got constant velocity all over the place, but we still had the turbulent quantities. And here the question was, what do you send in? And whatever you send in is going to decay down to 0 in the end anyway. And then I thought I had found some very nice setup here, but it turned out to be wrong. Let's see now. Gedit. The 0, yeah, let's take K for instance. So they had a very nice setup here at the inlet based on the internal field, I thought, and also this one, turbulent Ka. It turned out they are actually hidden here. So they have punched in the numbers inside an include folder and then initial conditions. So here the numbers were hidden. So no, it wasn't any fancy setup. So you might as well just punch in numbers here instead of these fancy dollar things. Meaning, what should you put in? For K, epsilon, omega, whatever model you choose, you have to put in something as a boundary condition. But remember the problem. I mean, this car is supposed to then move forward at a given speed, but the air he's hitting should then be actually still. So actually, it should be 0. But now these turbulence models, they don't like it when things are 0. So I would suggest you just put in a very small number and see what happens. So I tried it with 3, 30 and 300, and I got hardly any difference at all from the solution. Because for the, say, the real simulation, the flow around Donald and his car, there, of course, the turbulence is going to be created. But the background turbulence intensities should actually then be fairly low. So don't overdo it. Just use a small number. And it really doesn't matter how small. So 1 or 10, you will see also, and it should of course be investigated. Will this make any difference, or will it not? And yes, you should see then, no, you don't get much difference in the forces or the drag coefficient that we are seeking. Okay, any questions to then the exercise? Yep.
When running SnappyX mesh, how long should it take before the mesh is complete?
How long time does SnappyX mesh take before it's completed? Depends on how refined you want the mesh. So if you are, say, ambitious, you want a really detailed mesh, this is going to take forever. So hours. And something we are going to look at today then, run it in parallel. SnappyX mesh can be run in parallel. So that can make things much, much faster. But no, you have to be prepared. It takes a long time if you do it too detailed. Yeah.
I tried running it in parallel, and then it crashed because the mesh was bad. Does parallel have any like extra requirements for a refined mesh? Or is it just that it crashed faster because it's faster?
Yeah, it crashes faster because it runs faster. So he doesn't change anything logical with the mesh when you run in parallel versus on one CPU. That shouldn't change anything. You should get the exact same result in the end. So the reason that it crashed is you have specified too much, too high degree of details, I guess, and that's fairly dangerous. I mean, you find out, but no, it shouldn't take hours. So don't overdo it. Yeah.
How big do we make the mesh in the set direction, or we go like double the width of download, or?
No. So I recommended the following. The width in the Z direction. Let's see now. Where do we have? I don't have Donald here. He should be here somewhere, I think. Para view. Here we have download. So this is just the STL file, nothing more. And as you can see, he has a depth in the set direction already, given from the STL file I created. And the background mesh that you are creating, I would then suggest or recommend you create the background mesh with a set depth smaller than this one. So the mesh should be somewhere inside here. Because if you put it outside, then he starts meshing from, say, the end surface here, the front and the back, to inside that meshing. And you get additional cells, which in the end you're not going to need anyway, because we're going to extract it down to a 2D case. So keep your background mesh very narrow in the Z direction. I mean, you should get the information here. Let's see. If you go down here somewhere, you can put on, where are we, data access grid. So you get the size. And there also, you should get the information. So here you see the delta set go from, say, -5 centimeters to +5 centimeters. That is the STL file. Hence, your background mesh should then be narrower than that. So say ±3 centimeters, something like that. Other questions? That's okay. Now, let's have a look at the theory where we left off. That was multiphase flow. So we had looked through this, say, the theory behind multiphase flow, and yes, it's a very big area. So we are going to use this WOF method, the volume of fraction. So we have an alpha playing around with the different fluids. And let us then try to make some demos here. So WOF, the interform, that's fairly straightforward actually. You have a whole bunch of others, but we start easy. So let's try a tutorial. You should have a dam break case. So let's try that one. Let's see, where do I have my open form here? Somewhere, open form tutorials. And here I have something multiphase. And under multiphase, you see you have a whole bunch of different OpenFOAM programs. So it's a huge area here. But let's start easy. The interfoam. And under interfoam we have a nice laminar little case. It's called dam brake. So let's take that one. So we just take dam brake and I copy it, and let's go into that one. This one actually has been set up with 2 different cases. So as always, you should always check what's inside these all run files when you download a tutorial which have that file, just to see what the heck he's actually doing. And here he obviously does a lot. So he really yeah, almost dangerous. But never mind, we skip all that. Let's go into this dam brake case. So here, okay, there we have another old run. Let's have a look at it. Get the old run. Much simpler. So it's fairly straightforward. We have a block mesh, something called set fields, and then we run. So let's have a look at this setup. Try the block mesh first. And it's a fairly cute little problem. 2000 cells, not that much. And if we have a look at it, foam, whoops. Where are we? Apply. Then we have the outline here. So it's a 2D case. And we sort of have a small block down here. So you can easily see it has been constructed with 5 different blocks. It's very simple, uniform mesh, no problem there. And then we have this set fields thing. Inside your system folder here, you will then find a file which is called set fields dictionary. Let's have a look at that one. Set fields dictionary. gedit system set fields dict. And it's not the big one. So he has something that he wants to set. It's called alpha.water. Now that is this parameter that is going to be somewhere between 0 and 1. So if it's 0, then you have air. If you have 1, it's water inside your cell. If it's 0.5, it's 50% of each. So initially then he wants to set that one all over the place as a default value to be 0, meaning just air. But then we have one box. And here you have x, y, z points defining that box. And inside that box we are going to put alpha water equals 1. So the job with this set fields and set fields dictionary is to say set up an initial distribution, and here for this alpha water. You can use the same file actually if you want to set, say, velocities, initial velocities in different region in your computational domain. So there you could have set velocity 0, then you need a parenthesis and 3 numbers, of course, it's a vector. 0 by default, but then you could say the velocity is 1 inside a box or inside an area. And you could have several areas actually. So you can do a lot with this set fields. Now, if we have a look at the 0 folder here, you see we don't have it, but we have a 0 original. So let's have a look at that one. We have the U, and then we have not pressure, but we have P actually minus rho GH. What's that? Well, that is the pressure, but we have subtracted, say, the static pressure. And now it's a change. Normally when we operate with pressure in compressible flow, that is pressure divided by the density. That's not the case anymore. This is the real pressure in Pascal. So be aware of that one. And then we have a variable, our alpha. So this is also going now to be a flow variable or field variable all over your computational domain. And yes, it's dimensionless. So it's just a number between 0 and 1. So here we have sort of the boundary conditions for this alpha. Left, right, lower. These are going to be solid walls, so that's not a problem. But the top wall, that's actually an atmosphere, open to the atmosphere. And then he may go either in or out, depending on how the simulation goes. So if he goes out, so be it. But if he comes in, then you have to specify what's supposed to come in. So here, this alpha, say, variable, he may be pushed up through the ceiling, up to, into the atmosphere. But I mean, it's incompressible, so if something goes out, then something has to come in another place. And what's coming in? Alpha equals 0, meaning only air. So this means if you have some water splashing and then going through the top, then it's going to disappear into the unknown, into the atmosphere, and we will get air back. Of course, you could have changed this one to 1, and then it would be water coming in. Might be a little bit weird. You'll see when we start this simulation here. But the internal field, here everything is set to be 0 initially. But that's not what we really wanted, was it? So let's try this one. Let's see now. First, I have to make a copy of this 0 original into a 0 folder. I mean, OpenFOAM always looks for the 0 folder. So now it's copied. And the reason why you have a .original, you will see now, when we start first, well, we have created the mesh, and then I run set fields. So he's going to read this set fields dictionary file and then sort of set up the initial distribution. Set internal values 0, and then inside this box we set it to be 1. Now what has happened? Well, if you now look into the 0 folder, not the 0 original, but now the 0 folder, I made a copy of that one. Then you have the exact same 3 files. But if you look at the sizes here, this alpha water has become absolutely bigger. And here you see what he has done. The internal field is now a non-uniform list of scalars. And then you have 2,268 numbers between 1 and 0. So here he has sort of set up the initial state. At the end here you will find sort of the rest of the boundary conditions, as it should be. But the internal field has sort of been pushed into the 0 folder. That's why you have a 0 original, because if you do it several times, then you're going to mess up this one. So have a 0 original in the background. For the other files, the velocity, well, here's sort of a standard. You have just a solid wall, no slip there. And then the atmosphere, when we have a sort of special pressure inlet-outlet velocity. So it's fairly open. It can go either in or out. If he comes in, then we don't give him an initial velocity. And for the pressure, let's have a look. Here we go. Look at the dimension. This is Pascal, not pressure divided by density. Be aware of that one. And then we just say 0 all over the place, and we have a fixed flux pressure, as they call it. We could have used 0 gradients as well, should be possible. And then at the atmosphere, well, there we have a total pressure, 0. Fairly easy. Now let's try to run this case. And we have now set up everything, so it should be good to go. Interfoam. And it shouldn't take too long. Here we go. So what's he actually doing here? Yes, we have a Courant number. A little bit above 1. Okay, we can accept that one. And then we have something called mules. That is a sort of a fancy scheme for this alpha water. Fair enough. And then he solves for the pressure and the velocity, and no problem here. And he has created a whole bunch of result folders. Let's have a look. Parafoam. Here we are. So there you have not the 0, but the first time step. Let's include a 0 and then go all the way back to 0. So here we have the initial, then it doesn't have the pressure anymore. Velocity, constant 0. But you have an alpha water as a parameter here. So that one might be of interest. So there you see the initial state. So you have sort of a block of water here, and then you have air. So the idea is a dam break case, then there should be a wall here holding the water back. And at time equals 0, all of a sudden we remove the dam. So now this water should start splashing around, and then we have this little rectangle down here. So let's see how he runs. There you go. So yeah, you get a lot of splashing and action. And actually here, if you step carefully, you see his splash is quite high. And obviously here is something then that's going up and disappears. So some water here, we are going to lose it. So something goes out up here, and then we get air back. So the volume of liquid here is not going to be constant. So now I want to have a look at the velocities. So we start with 0, and then we run. Well, that was a little bit rough, wasn't it? Let's rescale him and run again. Looks rather violent, to say the very least. Why? Remember, he's solving the Navier-Stokes for both phases, both for liquid and for air. And yeah, you can have velocities here. You don't even see where is the boundary between the air and the water. You can't really see it. So typically, I mean, this will be velocity in air, and this will be velocity in water. Same goes for the pressure. I've removed the static pressure here. So playing around with that one. Well, that one is roughly only the water, but I think we have a pure P here. No, that's the pure water. Yeah. So you see, you sort of have both phases represented here. So that means to get an idea what the heck is going on is actually this alpha parameter that gives you the best idea of what's actually happening. The interfaces here, well, it's not perfectly resolved, of course not. We have a quite crude mesh here. So, as you can see, so it's rather coarse. And of course, with this WOF method, you can't have droplets smaller than one single cell. You can't handle it. So it's definitely not the entire truth, but come on, it's a model and it works. They had another finer version of it, but before we start playing around with that one, we are going to look into running things in parallel. When things get heavy, you should be able to use more than one CPU. Makes it better. Any questions so far? That's okay. Goodie. One thing with this case, to make it work, of course, we need something new here. And if you go inside your constant folder, you have an additional file that we haven't talked about. Namely, we need the gravity. Of course, we need the gravity. So here you then specify dimensions and the gravity. And of course, here you can have fun with playing around with the gravity. So say now minus there. Let's do this a little bit differently. I have a minus 6 in the y direction, and then I have 3 in the x direction. Okay, so now I have tilted the gravity. I've tilted the entire case. Why not? Let's try it. Should be possible. I think we can just remove the results here from list times minus rm and just run again. I mean, I haven't changed the mesh or anything, so interform. Here we go. So let's have a look at this one now. Apply, and then we had the alpha, and then we run. And yes, now the water is going to end up, say, in the down right corner, since I changed the gravity. And I mean, if you change the gravity, say, going in that direction, then he's not going to splash at all, but he's going just to flow out. I can show you. We have time to do that. Where were we? G. So I want to have minus 9.8 in the z in the x direction, and then I just put 0 in the y direction. Why not? And then we just remove the result and run again. Here we go, and then paraform. So what's going to happen now? You just get drains up, straight up, of course. No questions to that one? That's okay. Goodie. So far, the multiphase solvers using WOF. Now here I had also given you some material about running in parallel, so let's have a look at that one. Running in parallel. First question, how many CPUs do you have? When you bought your PC, then your salesman says, oh, this is a beautiful computer. You have many CPUs. Let's check it out. Let's check it out. You have a command called lscpu. That one definitely worth executing. lscpu. This is not a standard Linux command, but you have it in the open foam setup. So CPU family number 6 model, yada yada yada, and so on and so forth. So you get a lot of information here. And what is the point here? CPU family. What could believe that I had 6 CPUs? And then we have threads, and then we have core, and then we have sockets, and so on and so forth. So yeah, we have a lot of information here. Before we start understanding that one, in say the ordinary Linux world, you have a file under the folder proc. There you find a file called CPU info. Let's have a look at that one. Cat proc CPU info. This is standard Linux. So you always find this file. And this file, he will sort of be created when you boot up your machine. And there he will put in all the information that he finds of the different CPUs. So here you get a lot of information here, and how many megahertz, and the model name, and so on and so forth. But here he says processor number 7, processor number 6. So this might be misleading. Say now I want to flush this file out on the screen, but I just want to keep the sentences that contains the word processor. Then apparently, according to this recipe, I have 8 processors. Beautiful, 8. Typically what the salesman said to me, you have 8 processors. And that's a lie, I don't have 8 processors, I only have 4. Hence, using this CPU info might be misleading. So let's go back to this LS CPU. This is actually better. And you have some explanation for it here. So yeah, they're using what they call hyperthreads, something like that. So they sort of emulate that you have more CPUs than you actually have. And you shouldn't use them. So here, yeah, you have 24 CPUs. Beautiful. How many did I have? CPUs, where are we? CPUs, yeah, I have 8 CPUs, beautiful. But I don't. Because he used hyperthreads, and that is something that you really can't use. So the number of sockets here in this setup, you have 2 sockets, and you have 6 cores on each socket, meaning you have a total of 12 CPUs, physical CPUs, that you can use. But he can report the double, since you're using hyperthreads. And for my cheap old computer here, yeah, I have 2 threads, but that really doesn't matter. I have 4 cores per socket, and I only have 1 socket, meaning I have only 4 CPUs available. So think about that one when you check out your computer. You paid too much for it, obviously. Okay, so now we can split up our case. But don't split it up into more than the number of actual CPUs that you have. Of course not. So this hyperthread thing, you may actually address them. So yeah, you could have, say for this case here, he has 24 virtual CPUs, you might say. He could actually use 24, but it won't run faster. So 12 would be the maximum in practice. So, and why should we do this? Of course, it runs much faster. So that's the whole thing. you have some Amdahl's law and Gustafsson's law, how this should scale. So here you have the speed up versus number of processors. Ideally then, if you use 2 processors, he should take just half the time. And 4 processors, he should use 1/4 of the time. And in practice, no, you can't really do that, because when you split up a problem into several CPUs, they have to talk to each other anyway. So you lose some, say, efficiency there, of course. So according to Amdahl, this is going to level off, and then you can't really improve anything, even if you have more CPUs. That is actually not the real case here. You have another law, a weak scaling, Gustafsson's. It's actually a little bit better, so depending on how you define it. So OpenFOAM, they have done a decent job in doing the source code in C++ and the parallelization. So it scales actually quite nicely. So if you have access to 1,000 CPUs, well, it won't run 1,000 times faster, but not too far away actually. The way he does it, he's using MPI, message process interaction there. So the CPUs, I mean, they have to talk to each other. One CPU is just calculating part of the problem, but he's going to need what's happening at the edges. So he has to talk to the other CPUs. And there we use MPI. It's quite a standard way of running in parallel. And here, of course, you can spend a lot of time learning about computer architecture. If you have access to, say, a heavy workstation with 6,400 CPUs, or a supercomputer with 1,000 CPUs, then you might have to know how they are built. But I mean, learning hardware computer architecture, that is actually not our job. That's for some computer nerds to fix it for us. And sort of our compiler and our programs should just be able to access them and use them. But sometimes actually we have to know what the heck is going on. I know a lot of people there are actually not using the CPU, they're using GPU. CPU, computer processing unit. GPU, that's the graphical processing units. So they actually found out that the graphical part of your computer, he needs his own CPU. And this is for just integers, not real numbers. But they are normally faster than a CPU. And yes, they found out it's possible to use this for calculations as well. So the GPUs, they can actually be quite fast. And yeah, some programs can actually use on that one, can be used on that one. So for OpenFOAM here, as he said here, so yeah, they have been running OpenFOAM with 15,000 processors. That's a fairly decent supercomputer. So, and also, yeah, it's possible to run it on the graphical processing units, even several. So it can also be parallelized for that one. But as I said, this is getting tricky and sort of above our comfort zone. So we should just use it. To run in parallel, you have to do some additional step then. First, split up your domain. And when I say split up, not just logical, this is physical. So you tell the setup, we split it in, say, 4, and then you need 4 CPUs to deal with each of their own subdomains and calculate everything there. So that is what decompose means. And then when we are simulating, yes, we are using MPI. And then in the end, you will have a result split up into the number of processors that you have been using. So if you have, say, 4 CPUs, then you will get a result, not with one single file at the end, or result folders and stuff, but you'll have 4 of them. So then, typically you want to reconstruct it. You want to glue all these different solutions together to one. Then we are back to what's normal, you might say. So 3 steps instead of just simulate. That is the classical setup. And how should you split them up? Well, you have the command, it's called the decompose par. And he reads a file, the decompose par dictionary, in your system folder. And inside that file, you will typically tell him how many subdomains should we use. In other words, how many CPUs are you going to use? 128. I don't think any of you have that many, but I had only 4. And then the method, how should they be split up? And this Scotch method is widely used. I think it's because of this Scottish clothing, sort of with rectangles. So it's widely used method, actually. So that one is highly recommended. You have several other methods as well, but it can depend a little bit on your geometry. If maybe you want to just split them up, say, side by side in a one-dimensional line. That's also one way to do it. But the Scotch normally works quite well. So here you see, you have a whole bunch of different ways to do this. But the Scotch, as it says here, highly recommended. So yeah, we're going to try that one. So here then, just an illustration, you have a setup, flow around something. I think it's a moving flip, moving baffle or something. And then it's been split up into 4 processors. So each processor does his part of the job. And then decomposing, it's split up. And then when you want to simulate, you start with MPI run. And then the number of processors, and here it would read 4. And then your actual OpenFOAM program, SimpleFOAM, IcoFOAM, InterFOAM, whatever. And then you have to remember minus parallel at the end. Sort of has to be there. A little bit strange. But that is the setup for running it. And then in the end, you want to glue everything together. This is just then one command, reconstruct par. And this one doesn't have any dictionary files or anything, so he doesn't need any input. He can see for himself how many processor folders you have, and then he will glue them together into one. So it's not that many additional steps. So here you have it. Decompose par, and then run, and then reconstruct. So we will have a look at this one as an example after the break. Any questions?